Hello, I'm Mary Page Bailey, Senior Associate Editor at Chemical Engineering Magazine. Thank you for joining us for today's webinar, Pump Up Profitability by Minimizing Rotating Equipment Downtime. We hope it will be informative and useful for all of you. Any engineers and operators who are tasked with keeping rotating equipment online and operating efficiently should also be very invested in learning more about mechanical seals and the systems that support their long-term operation. Proper design and maintenance of mechanical sealing systems may seem daunting, but simple changes can drastically help to reduce downtime and avoid leaks. We will discuss some guidelines for maintenance and optimal system design of seals today. During the presentation, you will hear from Matt Dixon. He is an application commercialization manager with SwageLock. He has been with SwageLock since 1998 and throughout his career has amassed a wide range of experiences with high volume fittings, sampling systems, and much more. Thanks so much for joining us today to share your expertise. Just a reminder to the audience that questions can be sent in anytime during the presentation using the Q&A tab, and we will address as many questions as we can at the end of the presentation. There's also a handouts tab where you can download some supplementary information about the topic of our presentation today. So with that, I'll begin the program. You can go ahead and begin.
All right. Well, thank you very much for the introduction. I appreciate it. And I thank everybody for joining us today. So let's go ahead and jump into some of the material. Just a quick overview of the agenda for today. Do a quick overview of pumps and why the pumps and the seals fail. Talk about mechanical seal support systems in general. What are the main functions thereof? And then talk about ways that we can optimize the design of those seal support systems, make them a little bit more effective and a little bit more reliable. And then we'll go through some of the resources that are available to you and that are also available to the SwageLock sales and service centers that can help you out with your seal support systems. So first of all, let's talk a little bit about pumps and why they fail. So here is a chart that came out of a leading publication for pumps, and it kind of gives an overview of what is the mean time between failure on average for for different industries, different locations, different facilities that maybe have different focuses. And as you can see, it really ranges quite a bit. So for example, there's one repair focused refinery there in a developing country where their average their mean time between failure on pumps is only 1.6 years. So every 1.6 years on average, a pump is going to go down and they need to fix that. And of course, there's not only the cost of repairing the pump associated with that, but then also potentially lost production as well. Contrast that to the best class petrochemical plant in the United States in Texas of over 10 years. So there's really a wide range of mean time between failures. Now, when we're talking about failures of pump, there's a bunch of different things that could potentially contribute to what it is that's causing that failure, what different components that could be failing. One of the main ones is actually the seals. So with the mechanical seals, of course, the mechanical seal creates the seal between the pressurized pump housing where the shaft exits and seals to the atmosphere. Now, when we're looking at what is good, what is best practice, what is industry standard for mean time between failure for a seal, you could see that our average is about 70 months. So if we're really looking to target 6 to 8 years on a seal, that's really what we're looking to do. Get a good life out of that seal. Now, some 90 months, like for example, that best in class petrochemical plant. Again, they're well in excess of that 90-month target for being excellent. And then if you look down at the poor end of the scale, 62 months or about 5 years. If you're below that, you definitely have some room to improve. And there are ways that we can do that. Now, looking again, at different components, different things that might fail within that. Seals, of course, the two numbers there correspond to, either refineries or the, other chemical plants or petrochemical plants. And notice that the refineries tend to be a little bit longer. Now, why is that? Well, there's two different reasons. One is that, the refineries tend to use API pumps, which are a bit more robust. And secondly, refineries tend to have more stabilized processes in terms of constant pressures, constant temperatures. Compare that to chemical plants, which are very often going to vary those pressures, those temperatures, have temperature ramps, and more of a batch processing type of an operation as opposed to continuous process. So as a result, it's a bit harder on the pumps, and as a result, they end up with a lower mean time between failure on average. Now, all of that also can play into the life of the couplings and the bearings and things of that nature as well. So overall, each of those individual components has the potential to fail. Now, regardless of what facility you're in, you're probably going to come across this list. This list is a list of bad actor pumps. So these are the pumps in the facility that, for whatever reason, are continually failing and are where the rotating equipment engineer spends 80% of their time on these pumps. So here's an example of one, of this list at one particular refinery. We've got pump 20143, pumping crude. And you can see, summarized here in the last 5 years, they've repaired this pump 12 times in 5 years for an average lifespan of only 4.6 months. So my goodness, this is really a bad actor pump. The in this case, they've spent $94,000 repairing this pump, and again, that's just the direct repair cost, and that does not include any potential lost production time as a result of that. So, there's a lot of different reasons that this could be happening. For what, there are, different efficiencies that you can have in how you operate your pump, and those can contribute to, the life cycle of the pump. Now, in this case, the latest failure, the root cause of that latest failure was that they lost their flush fluid in their seal support system, and as a result, they have a plan to install a Plan 54 seal support system so that that particular failure doesn't happen again. But if they're failing every 4.6 months, there are probably lots of other problems that they could potentially fix as well. So why are pumps failing? Well, if you look there at the biggest piece of that pie, the blue chunk, you can see that that is a shaft seal. Again, any sort of symptoms that you have in the operation of your pump, negative symptoms, they're probably going to impact the life of your mechanical seal as well. So if you've got vibration, if you've got misalignments, if you've got cavitation, all of those can translate into a reduced life in the seal, of mechanical seal as well. So that's really where we tend to focus a lot. So you do have some other failures. So of course, roller bearings there being another big one, and also some impellers. Maybe that's a relatively minor one. Could be cavitation that's eating away at your impeller. But again, the two big ones is the roller bearings to a lesser extent, and by far the biggest is your mechanical seal. So why do seals fail? There's a lot of different reasons why that seal could fail. Maybe the pump was allowed to run dry. When you first started the pump up, was there actually liquid in that pump? Or it could be that they lost flush fluid at some point, and maybe the seal doesn't fail right away, but maybe you have, by running it dry for momentarily or for some period of time, you have just decrease the lifespan of that seal. And so as a result, it will fail quicker than it might have otherwise done so. We also have potential contamination. If you have a dirty process and you've got contamination flowing through that, how do we control that contamination and keep that contamination away from the seal faces? Well, we can do that with seal support systems. So using flush fluid that's nice and clean to flush that contamination away can definitely help prevent that contamination from impacting the seal life. Operator error, so improper commissioning of the pump. So, for example, if they did not bleed all of the air out of the system when they commission the pump, it could be that they now have air in the system, and that could impact that as well. Vibration, we talked a little bit about vibration, how that could potentially impact the seal and the bearing life. Wear and degradation of O-rings, lots of different reasons here. I won't go through all of these, but really there is so much that can go wrong here. We really got to get it right in order to get that seal life up. But the mechanical seals, they are one of the most vulnerable, you know, parts of the pump, and you might even call it a canary in the coal mine, and that a lot of the it's really indicative of problems in your pump, whether it's misalignment or vibration or what have you. All right, so let's take a look at pump curves. You've probably seen these before. They look a little bit different if you're in Europe or maybe in Asia. But here in North America, you're going to see these combined pump curves. And when we're looking at where our pump is operating on the pump curve, you've got the pump head on the left, and you've got the flow rate along the bottom. And we really want to be in kind of that Goldilocks zone there in the middle, where that's really where we can have the best efficiency. That's where our pump is going to be happiest, where we're going to see a minimum amount of vibration. We're going to avoid that cavitation. We're going to avoid that shaft deflection, those temperature rises. We want to be as close to that best efficiency point as we possibly can because we're going to avoid those issues. And as a result, we're going to potentially extend the life of our seals because we're not going to have those issues translated into reduced seal life. So when we're looking at a pump, we really want to stay in that middle because that's going to allow us to achieve as close to the design life as possible. So theoretically, if we were right down the middle, maybe we could achieve 100% design life. If we're a little bit farther out away from the middle, maybe it's only going to be 75% design life. And again, this is really only for illustrative purposes. I'm not saying if you're a little bit off center that you're going to necessarily degrade your performance by 25%, or in this case, 50% if you get farther and farther away. But just understand that the closer you are to the middle, the better off you're going to be in terms of the design life of your pump, the operational consistency and reliability, and your pump is just generally going to be happier if it's operating there towards that closest to that best efficiency point. So let's take a look at the mechanical seal support system. Because when we're looking at seals, the mechanical seal support system is an essential piece in order to keep that mechanical seal operating appropriately. So mechanical seal support systems are defined by API 682, much like the seals themselves. And what they're designed to do is to deliver a liquid or a gas to the seal chamber or to the space between two seals, or possibly on the outboard side of the seal in order to do a number of different functions. We're looking to uh, we're looking to make sure that there is a fluid film between the faces of the seal. Now, that could be a thin film of liquid, it could be a thin film of gas, but we want to have that film between the rotating seal face and the stationary seal face in order to reduce that friction and control that heat. It also helps control the pressure in the seal chamber. So being able to control that pressure can help you to control that fluid film and can help you to control the leakage that actually gets past the seal. I mentioned the temperature as well. So it helps, having a flush fluid in there, for example, helps you to flush away the heat, helps you to flush away contamination and dirt. Again, if you have a dirty process, using a nice clean flush fluid, whether that's filtered or whether that's some external flush fluid, helps you to keep that contamination away from the seal face, doesn't allow that contamination to build up in the springs or, God forbid, between the seal faces, and really helps you to maintain that seal integrity. And then, ultimately, of course, it helps to prevent any system fluid from leaking to atmosphere, whether that is by maintaining that seal in good working order, or in the case of some seal support systems, we're actually helping to collect the leakage on the outboard side of the seal, and that helps us to, again, control that leakage and if there is leakage, and there will be some leakage, but to maintain that and control that in some way. All right, so we're going to take a look at a Plan 11. This is one of the basic flush plans that we have in the in this that's defined by API. With this, you're actually using the pumped fluid on the discharge side, and we're flowing back through the seal and into the seal chamber. You can see how that flush fluid goes right past the seal faces there. The seal faces being the yellow seal face, which is rotating with the shaft, and the blue seal face, which is fixed and not rotating. But it flows past, and it actually then will flush away any contamination. It'll carry away any heat, and we're just again using that pumped fluid. So that's a really good example of a very basic seal support system that we can that you know very common seal support system that's used out there on a lot of different pumps. Now let's take a look at the Plan 50, a different type. It's a Plan 52. With a Plan 52, what we're actually doing is we're actually using a fluid that goes between two seals. So we can actually see there are two seals in this case. You can see this two sets of yellow and blue seal faces, and we're actually relying on the thermosiphon effect to circulate that fluid between those seals. Again, flush away any heat, keep that nice and clean. And when we're talking about the thermosiphon effect, what we're talking about is actually where the principle of how the warm fluid will rise. So the fluid will the warm fluid that's in that seal chamber will rise up and go back to the seal pot, the pot that you see there on the right, or it's labeled as a reservoir. There's a cooling coil in there. So that cooling coil will cool that fluid down, and so it will go down back down through the piping and back to the seal. And so it circulates just by using that heat differential. Now, there is very often a pumping ring that's actually affixed to the shaft of the pump as well. And what that does, that also helps to circulate it, but it doesn't really provide a strong motive force. So between the thermosiphon effect and also the pumping ring, we're really relying on two relatively weak forces to circulate that fluid. But this Plan 52 and very similar Plan 53A both use the same methodology and are both very, very common seal plans for dual seals like this. All right. The next one we're going to look at is actually on the outboard side. So this is actually a Plan 62. Well, with a Plan 62, we have uh, we are actually on the outboard side of the seal. So this one happens to be a quench plan. With a quench plan, you're removing contamination from the outboard side of the seal. So imagine you had a hot, dirty process, and maybe you have some coking on the outside. So this would actually help to cool. Ironically, you would often use steam to help cool that down. So you imagine this is a very hot process. So in that case, we're helping to prevent that coking from happening on the outside. Another use for a plan, maybe not a Plan 62, but another similar one on the outboard side of a seal would be a leakage collection plan. So using some fluid or some piping to be able to help collect any leakage that actually does make its way through. Now notice in here that we actually do have a port on our seal for a flush. You can see that there at the top of the seal, right by where the flow comes in for the Plan 62. It's very common that you would actually have multiple seal support systems on a given seal plan or on a given seal. So in this case, you probably wouldn't have just a Plan 62, but you would also have a flush plan of some sort, very similar to the Plan 11 that we just looked at a little bit ago. And likewise, with the Plan 52 that we looked at, very often you're going to have a flush plan associated with that. So it's very common that you'll actually see two seal support systems or seal plans on a given seal, sometimes even three, depending on the application. Okay. Let's move on. So let's talk about how can we optimize the design of those seal support systems in order to make sure that they don't have too many maintenance concerns or operational concerns. So first of all, we want to make sure that we can minimize the number of components. The fewer components, the fewer things there are to go wrong, the fewer things that there are that can possibly leak. So the fewer components that we can have, the better. The fewer number of connections, the better. On the converse of that, though, we do want to have as much instrumentation as we can so that we can help diagnose those pump problems. Not just when we have a problem, which of course is helpful to be able to see, all right, what's my seal chamber pressure? What is the flush pressure? Things of that nature. That is helpful to help diagnose those pump problems when you have an issue, but then also to help troubleshoot, or sorry, to help predict those problems before they come up. Imagine if you had a dashboard, if you will, of instrumentation associated with every pump, where you're seeing the temperature of the seal chamber, you're seeing the temperature of in and outs, you're seeing the pressures in multiple locations, and you know where those things are supposed to be. And at a glance, you could tell if those pressures or temperatures start to change. Maybe we're about to see some sort of a seal issue or a pump problem that we need to address. So it'd be great to have as much instrumentation as possible. And API 682 actually emphasizes this point. With the fourth edition, it actually moved away from things like pressure switches and move more towards things like pressure transmitters so that we have more information available to us. We also want to design these things for maintenance and make sure that they're relatively simple to operate. So make sure that it's easy for the operator who has to interface with the system to understand what's going on, and to make sure that the components that we select are optimized for that particular application, and for the for use in a seal support system. All right, let's talk about some of these points. One of the things that we have to concern ourselves about, especially when we're using when we have like a Plan 52, like we looked at, where we're relying on that thermosiphon effect or a pumping ring, we want to avoid flow restrictions wherever we can. So as a result, we're going to use relatively larger diameter tubing. So where a flush plan might use a half-inch diameter tube, one of those Plan 52s or a 53A might use 3/4 inch or maybe even 1-inch tubing, just to reduce the flow restriction. Because again, that thermosiphon effect, that pumping ring, it doesn't provide you with a lot of motive force. So to that to that end, we're also going to eliminate elbows wherever we can, because not only will the 90-degree elbow restrict the flow to some extent, but it's also an additional connection. So that's why when we're building these systems, we like to use tubing, because it allows us to bend the tubing very easily, avoid the use of the elbow, and now we've got a nice smooth tube bend that doesn't restrict the flow as much, and that's eliminates some connections. Likewise, when we're flowing through these systems, we want to avoid that right turn through a T as well. So if you've got a T in your system, which is fine, you're going to have that for instrumentation, things of that nature. We generally want to flow directly through from run to run of the T as opposed to flowing through the branch of the T. Now, when we're looking at seal support systems, in the old days, they tended to be made of pipe, typically half-inch Schedule 80 pipe, and they ended up with a lot of threaded joints. Especially, you can see a bunch of elbows that are here. So we've got elbow here, elbows all over the place. These are all leak paths, potential leak paths. And so we want to avoid those if we can. Not only the potential leak paths, but again, depending on the type of seal support system, they could be restricting your flow in such a way that could impact your performance as well. Um, and you notice here that these things are pretty rusty. Very often these things are made out of carbon steel. So you're going to have to maintain those in some way, whether you're maintaining some sort of a surface coating like a paint or something like that, or maybe you just have it on a preventative maintenance schedule to replace the rusted components on some time frame. So old pipe systems, in general, people are moving away from the old pipe systems and moving more towards tubing systems. Now, tubing systems that actually became, officially sanctioned in the API standard with the third edition, which came out, I believe it was in 2004. So almost 20 years now. And that's really a nod to the fact that people had been started using tubing systems in these, in these seal support systems a long time ago, for many of the reasons that we talked about. It's easier to have those bends. Tube fitting connections are more reliable than pipe thread connections, and you're able to minimize those connections by smooth tube bends. Yeah, you can bend pipe or weld pipe, but not everybody has those capabilities, and so as a result, you did end up with a lot of those threaded joints in those piping systems. Now, we have to acknowledge, of course, that tubing is not going to be as robust, mechanically as robust as piping. So as a result, the API standard actually recommends you use a heavier wall tubing than you might otherwise need for the pressure of the system. So, for example, with a half-inch tubing, they recommend an 065 wall tubing. Now, most common size of half-inch tubing, of course, is 049 wall, and that's going to get you, more pressure than you probably will ever need in these systems. But just for mechanical rigidity, mechanical, robustness, they're going to recommend a heavier wall. And the same is true of the 3/4 inch and the 1 inch tubing sizes that they list. Still commonly available sizes, but heavier than the average wall thickness. All right. So when we're looking at other ways to make our seal support systems better. Of course, one of the things we have to look at is safety. And one of the things that comes to mind with seal support systems is maintaining our seal pots. Now, with the seal pots, again, we had that fluid that was flowing between the two seals and, to and from the pot. Now, we're going to eventually lose some of that fluid either in one direction or another. We're either going to lose it to the atmosphere or we're going to lose it to the process. It's potentially that we could potentially over time leak inward through the seal into the process. And so we need to have a way of filling up these seal pots. Now the API standard actually defines that your seal pot has to be sized such that you have 28 days of operation worth of fluid in that. So that's fine. We shouldn't have to do this every day. But when we do it, we need to make sure that we're doing it in a safe way. So the old traditional way was to get on a ladder, put it up to the top of the seal pot because the seal pot may be, you know, it could be 6, 8, 10, 12 feet in the air. So you need a ladder to access the top. You cool everything down, you shut everything down, you depressurize, you open up some sort of a bung or a plug, and then you pour in the oil or whatever it is that you're using as your barrier or buffer fluid into the seal pot. Okay, so we can do that, but getting up on a ladder, that's potentially dangerous. Now we're carrying some liquid up onto that ladder. We really, there's high temperatures, there's potential pressure concerns, so we really want to avoid all of those considerations altogether. So one way that we can do that is by using a fill tube assembly. So the fill tube assembly you see there on the image on the left is basically an assembly that allows you to pump fluid into the seal pot from grade. And again, this is now a requirement within the API standards that you have to be able to fill these seal pots from grade. So they don't want you getting up on ladders anymore just because of the safety concerns. So being able to couple a quick connect up there, pump a little bit of fluid to top off the seal pot. This is a great way of of filling up your seal pots. And the way you can do this, and a way of getting fluid to the seal pot, is by way of a fill cart. So, for example, you can go down your row of pumps. Very often, of course, pumps are grouped together. So you can go down your row of pumps and go from one seal pot to another with a seal cart, sorry, a fill cart like what you see on the left or on the right, and use a hand pump to you couple up to that fill tube. Use a hand pump to pump the fluid into the seal pot. So it's a really nice, effective, convenient, and of course, safe way of filling your seal pots. So when we're looking at safety of a seal pot system, this is one of the first places we look is how do we fill those seal pots? Because very often, again, people are still using that older methodology. Another way of improving, our system is by way of instrumentation, and thermal wells are definitely, thermometers are one way of improving that. Our knowledge about the system. What is the temperature of our system? And anytime you have a thermometer, you generally have to have a thermal well, and with that, a thermal well T that allows you to measure that fluid temperature. Now, traditionally, thermal well tees are welded monstrosities, kind of like what you see here, and I don't mean that in too negatively of a way, because certainly they're good construction and certainly they're effective, but they are a lot of work, and as a result, they're fairly expensive. So if you look at the thermal well tee on the left there, in the we look at the number of welds that you would have. You'd have a weld up here, one, saddle weld two, three, 4, 5, 6, 7, 8, at least 8 welds on this particular thermal well T. Then you've got the thermometer that goes down into the thermal well, which is attached on a flange. So a lot of work that went into building this thing. And then installing it, of course. The one here on the right, again, we've got a lot of welds. You got one, two, three, four, 5 welds right there. So a lot of welding time. You've got to have the expertise. And here, the thermal well is just threaded in with a pipe thread connection. Now, suppose that somebody went to actually replace the thermometer, and they put a wrench on this to go replace the thermometer, and they put a wrench on the wrong thing and actually started loosening the thermal well. What's going to happen? Now all of a sudden you have a process leak. You're leaking the fluid out of your seal support system as opposed to instead of just removing your thermometer. So, these thermal LTs can definitely be a problem. We prefer a more compact and smarter approach, which is a thermal well T that's either made out of a pipe fitting or in this case, a tube fitting, where you have the thermal well that is permanently welded into place so that you can't accidentally loosen the thermal well. So in this case, you can see we've got a T here where the flow would normally just go straight through. We've got the thermal well that gets first threaded down into the branch of the T and then back welded in place. Again, that way you can't accidentally loosen it. You're eliminating a leak path. So we're eliminating those, leak paths in your seal support systems will just eliminate headaches. There's also an angle pattern version of this, but again, remember that in those systems that rely on the thermal siphon effect, maybe the angle pattern isn't the best choice because that is going to restrict your flow a little bit more than a straight pattern would. So we're generally going to steer towards a straight pattern versions of these. Another way to reduce leak paths is by using what's called an extended male connector. With these tubing systems, generally you have to interface with the seal in some way, of course, and the seal generally is going to have some sort of a pipe thread connection on it. Okay, well, that pipe thread connection is usually down inside the cage or inside the shroud of the pump itself. So if you were to use a normal tube fitting male connector, which is relatively short fitting, so imagine you had a fitting that was only about that long. In that scenario, you don't have enough projection of that fitting outside of outside of the cage of the pump in order to be able to get a wrench on the tube fitting nut to attach your tubing. So how have people traditionally solve this? Well, this is how they've traditionally solved this is with a pipe nipple and then a female connector instead of a male connector. Now, not everybody has a female connector, so very often what you'll see is a a pipe nipple with a pipe coupling and then a male connector as well. So as a result, you actually have 3 pipe threaded connections instead of 2. Or in this case, we can actually use a extended male connector like what we see here on the right, and we're eliminating some of those pipe thread connections. Now we've just got the pipe thread connection that goes into the seal and then the tube fitting connection coming out the backside. All right, so let's look at an example of a seal support system here. So this one has a few problems. So first of all, we've got an orifice, which is pretty common. But how do we know when that orifice is clogging? On this flush plan, how do we know? We don't really know because we don't have any instrumentation. And if we wanted to add instrumentation, this particular one is made with welded pipe, so it's going to be pretty difficult for us to cut in and add instrumentation. Now, Another one, another issue here is where the hose enters the seal. How many pipe fittings do we actually have in this case? My goodness. We've got a threaded JIC type connector here, got another pipe thread connection here, pipe thread connection here, another one here. And then what we can't see is where it actually threads into the seal itself down here. So we've got 5 different connections, all of those different potential leak points where it comes, where we're transitioning from this hose into the seal itself. So a lot of different leak paths that could potentially be avoided if we use something like that extended male connector that we were just looking at. All right, and then of course the hose itself. The API standard actually does not allow for hoses. This should all be rigid piping or tubing, as it were, to avoid things like what you see here, uh, where our hose is actually kinking. So I can't tell you when that hose is going to fail, but I can tell you that it will fail. So eliminating things like that is definitely something that we want. Is something that we want to do to make sure that our systems are more reliable. All right, let's take a look at this plan, Plan 72 and Plan 76. This is a combination plan. So the picture on the left is actually, the existing panel that we were replacing, and it's not too bad. It's fairly well labeled. It's got some instrumentation on it, not too bad, but there's definitely some room for improvement. For example, you can see the plan on the left there. Instead of pressure transmitters, we have pressure switches. So we don't have as much information going out of the panel as we might otherwise have if we had like transmitters like the one on the right. We've also got, nice features on this panel to make it a little bit more intuitive for the operator. So for example, in this case, this one happened to be an area where I think in the ISO stripper where the what was coming out of the pump could potentially have some corrosive effects. So part of the seal plan needed to be made out of Manel, but of course we didn't want to make the whole thing out of Manel because of the expense of it. But we made it very intuitive on the panel what portions were Manel versus which portions were stainless steel. So this is a nice thing from a maintenance perspective, so you don't accidentally put the wrong components into the wrong areas. I mentioned the pressure transmitters. That's an area where we were able to improve this system. Got the tube fitting there circled on the left. Those tube fittings actually have the little dabs of wax on them, so we can see if they've been tampered with, if somebody has loosened them. And look just to the left of the pressure regulator there. In this case, we've got a vinyl wrap on the panel where everything's labeled. In this case, we've actually got the regulator set point labeled on there as well. So a lot of information on the panel itself makes it really intuitive for the operator who's interfacing with this system. All right, so here's another one that could have some improvement. So this one happens to be a Plan 32. With a Plan 32, you're using an external flush fluid, and very much like a Plan 11, but instead you're supplying that flush fluid from not from the pump discharge, but from some external source. So with a Plan 32, in this case, we've got our flow coming in from the top through this hose. It comes up into this flow meter, and then through our through our strainer, got a hard 90-degree elbow, and where we are regulating our flow with a throttle ball valve. So, and all of this just kind of hanging there. Now, anytime somebody sees a ball valve handle, somebody's probably tempted to actuate that thing. So, uh, you know. Our philosophy is one, you don't ever want to throttle a flow with a ball valve because they're just not designed for that. They're really designed to be open closed valves. Two, if it's just hanging around like this, people tend to be more tempted to fiddle with it and mess around with it. Whereas opposed to if it's on a panel like this, um, you can, it looks more like a system and people are more hesitant to mess around with it if they don't know what they're doing. So moving it to a panel really tends to be a nice effective strategy for one, making it easier for the operators, two, making sure they have the right components like this needle valve to throttle the flow instead of a ball valve, and three, making the random person less likely to come and mess with it. And here's an example of a Plan 32 that was installed on a pump. So you can see here we've got a We've got a strainer, and that's filtering out anything in the flush fluid stream. We've got a differential pressure gauge on there, so we can know when that strainer is starting to get loaded up. And when we need to go ahead and maintain that, we've got a bypass, so we can go ahead and bypass around the strainer while we're maintaining that. So it's just a really nice way to present this. And again, we've got the vinyl wrap on there with everything, everything labeled. Makes it nice and easy for the operator to understand what's going on, where everything's going, and what everything is. All right, so what are some of the resources that are available to you, either on your own or through, or through the SwageLock Sales and Service Centers? One is an application guide. So SwageLock, we actually publish an application guide where we talk about all the different seal support systems. You can find this on swagelock.com. So this is a really nice, handy tool to summarize what each of the systems does, what the schematics look like for each individual system, and what components are involved. At SwageLock, we also sell kits and assemblies, for seal support systems. So this is handy for you in a turnaround. Say you can have a kit of components on the ready if you're getting ready to change a seal support system. So you can get an assembly. Maybe it's in this case, what you see there on the left, where we've got an accumulator and a cooler, and then a kit of components to go along with that to help hook it up to the pump itself. Again, during that maintenance interval. So, we have those available, and those are all specifiable by part number. So it's very nice, easy system for us, trying to enable you guys to make these changes and maintain your pump systems on a really easy basis. Within that application guide, again, we do have those part numbering structures that define all the different components and such. And it could be something like really simple, like this kit for a Plan 11. And we looked at that video, the Plan 11, again, where the fluid was coming on the discharge side and then going back into the seal chamber. In this case, just this really simple tubing run, maybe with one of those extended male connectors and a flanged connection on the discharge side of the pump. So this is again a very easy way to help specify and have those components on hand when you need them during a maintenance interval. At our sales and service centers, we've got tools to be able to help provide you with, with all the quotes that you need for individual kits. We've got bill of materials generators that provide outputs based off of those part numbers. We've got configurable CAD files that help us to generate CAD images for you to help your installer so they know exactly what it's supposed to look like. So here's an example of a Plan 52. A drawing that was prepared by one of the SwageLock sales and service centers. So we've got the kind of a schematic view on the right-hand side there showing some of the details of the seal pot itself, and then how it actually connects to the pump, showing the tubing runs, etc. And then there on the left, you can see where we actually built those seal pot assemblies and provided them to the site so that they could be installed, as necessary. So this is just an example of how SwageLock can help out with these seal support systems, both on as the system's being designed, help you to design those systems better, but then also help you on the maintenance side of things as well, in making sure that as you're replacing those systems, you can do so effectively, you can do so efficiently, and you're going to make sure that you have all the materials that you need on hand. And that's part of the benefit of having that local SwageLock sales and service center. Being able to support you on sites and being able to support you at the local level as opposed to coming from a distant factory like I am here in Cleveland, Ohio. Right, so that's all the content that we had today. If you want to learn a little bit more about this, you can expect to receive an email with a link for more information. You can also go to the SwageLock website, swagelock.com, where we've got a blog, SwageLock reference point, with more information, about various different topics, including seal support systems. And of course, social media. This WageLock is very active on LinkedIn, Facebook, Twitter, etc. So by all means, come visit us on social media. Yeah, yeah. So definitely, we're here to help, and we're looking to help you out in any way that we possibly can. So again, thank you very much for joining us today. And we're at this point, I'm going to turn it back over, and we're going to address any questions that you guys might have.
Hi, thank you so much for that presentation. I think that was great. I think it had a lot of very practical information for our audience. We'll enter the Q&A period right now. I also want to direct our audience to the handouts tab where they can get some supplementary information, and then also just encourage everyone to stick around because there will be a short survey at the end of the presentation. So we have had quite a few questions come in. I think this will spur some insightful discussions. So I'll just start here. Somebody is asking, why is the minimum tubing bend radius so important on seal support systems?
Yeah, so the minimum bend radius on seal support systems, that has to do with, again, that thermosiphon effect and that pumping ring that we were talking about that I mentioned, where you don't have a whole lot of motive force to push that fluid through that circuit, through the seal pot, um, through the seal chamber, etc. So you want to reduce the flow restriction, and one way of doing that is to have nice gradual tube bends as opposed to elbows or as opposed to sharp tube bends. So, when we're talking about tube bend radii, there is a no hard fast rule in terms of minimum bend radius. I would say at least a 3 times diameter bend radius, but the larger the better. Very often you'll see people bending the tubing over their knees, on something like that, or over a 55-gallon drum or around a large diameter pipe in order to get a really nice large gradual bend. So, but the reason for that, of course, is to minimize the flow restriction that we have.
Yeah, great. Thank you. I think that
Mhm.
that answered that very well. We have somebody asking, do you have a rule of thumb for the number of pumps needing seals that make it more cost effective to use individual seal pots versus a centralized seal water system? Kind of interesting.
Yeah, so one of the things that you can have is like a Plan 54 or Plan 55, which is kind of an external system that pumps fluid between the seals of a pump. So where you might have a Plan 52 or a 53A, where there's a discrete system on an individual pump or an individual seal. The Plan 54, Plan 55 is a centralized system, and it could serve one or many pumps. I wouldn't say that there's necessarily a rule of thumb in terms of the number of pumps. Certainly, we've seen a lot of systems where Plan 54 or 55 services a single pump or a single seal. But when you're investing in a system like that, generally you're going to have more pumps attached to it because it is because of the expense of it. Now you have to balance that, of course, against the maintenance implications. So if you have to maintain that Plan 54 or 55, now you're not just taking down one pump, but you're taking down multiple pumps. Or if that system fails, you potentially have multiple seal failures as opposed to a single seal failure. So, is there a rule of thumb? No. It's really just a balance of the cost of the system versus the likelihood of maintenance versus the implications of what happens when you have to maintain that or if something goes wrong. So those are all just it's just a balancing act.
Mhm.
It's I would say the number of systems that I would typically see on something like that would be in the neighborhood of 5 to 10, but it could be more, it could be less.
Yeah, great. Thank you. It sounds like there's a lot of factors that go into considering something like that. We have somebody ask, with a Plan 32 system, what is typically used for the external flush fluid?
Yeah, so because that external flush fluid ends up in the process itself, it has to be obviously compatible with the process. So what you'll often find is you're using some sort of refined product that's coming from downstream in the process. So for example, in a refinery, if you're pumping crude oil and you need an external flush fluid, maybe you're taking one of the refined products from downstream. So you're taking the gasoline, for example, and pumping that back into the system because again, that ends up into the fluid stream, the pumped fluid stream. So yeah, it could be like something like that. One of the metaphors that we like to use is if you're pumping ice cream, maybe you're going to use milk. So again, it has to be something compatible. It could be something external, but Plan 32s tend to get kind of expensive because you're again using that fluid at some flow rates, and that's fluid that you could otherwise sell, or it's fluid that you now have to purchase. So we try to minimize their use, but they do have a definite niche application, and in those cases, you're generally using something refined product downstream.
Yeah, great. It's very interesting. So we have somebody asking where the orientation and the location on the pump discharge piping should the seal flush originate from from pump supplied systems.
Yeah, so typically it's directly downstream. Normally, you just have a branch connection right off of the discharge piping. I don't think there's any rule of thumb in terms of number of pipe diameters downstream or anything like that. Just immediately downstream of the pump. In fact, some of the seal plans actually have that internal to the pump itself. I believe that would be like a plan 1, 2, or 3, where it's actually that flush pipe work is actually cast into the pump casing itself. But if it's external, basically immediately downstream of the pump, the discharge nozzle, you're going to see some sort of a branch connection, and then it goes right back into the seal itself.
Yeah, we had another question come in asking about the seal flush as well that says, some plans have seal flush from the pump casing. When is this setup acceptable?
So it's that's really a feature, I would say, of the pump itself, because it really is taking the place of an external flush. In those cases, the pump manufacturer has decided to go a little bit above and beyond, if you will, to integrate that feature into the pump. I wouldn't say that there is necessarily an application for one of those over another. So I, I don't know that there's a case where having that internal flush is more acceptable than having an external flush. I think they're both generally providing the same functionality. It's just a question of whether your particular pump has that or not. Ultimately, it's going to be the decision of the seal manufacturer. Seal manufacturer is generally the one who is specifying that seal support system for that seal. What's going to be most appropriate? What's going to be most effective at maximizing that seal life? So as long as they say it's okay, I think it's fine. But from my experience, an external flush versus an internal flush, they're really doing the same thing, and so we don't really need to have a hard and fast rule in terms of when to use one over the other.
Okay, great. So we have time for a couple more questions. We still have some coming in. Somebody has just simply asked, what is the most common type of seal support system that you see used?
Definitely like a Plan 11. That first flush system that we saw. Very often, that's going to be the only seal support system that you're going to see on a single seal. And you so Plan 11 is by far the most common. After that, you can get into some like the Plan 52 that we saw with the seal pot, or similarly a Plan 53A or 53B are very common. 53B is very common, especially in Europe. So it depends where you are, but Plan 11 by far is the most common that you're going to see all around the world.
Okay, great. Somebody is asking, what kind of fluid is used in the bladder in the seal pot arrangement?
Yeah, so in a bladder, in the system like a 53B where you have a bladder accumulator, um, that you're going to use the same fluid in that as you would in like a 52 or 53A, which are your seal pot systems, and it's going to be generally like a hydraulic oil. I forget the name of it. It's a something purple is very common, but yeah, it's just a hydraulic oil that circulates through, and of course, it does have to be. It does have to be again generally compatible with whatever it is that you're pumping, because you're going to have leakage in one direction or another. Either depending on the system, it could be leaking out into your seal support system, or it could be that your barrier or buffer fluid, your barrier fluid, I guess would be leaking into your pumped fluid, and very very minute amounts, of course, but it could be potentially into your process. So you need to really evaluate that to make sure that any sort of leakage into your process isn't going to affect you.
Mhm.
But generally, it's going to be some sort of a hydraulic oil.
Okay, great. Thank you. That's a very informative answer. We have time for maybe a couple more questions here. I'll go ahead and ask. Somebody wants to know what is recommended to minimize microbial contamination in an ultra pure water system.
Oh, that's actually a new one for me. Yeah, I've not had a lot of experience with this, but I would expect that things like ultraviolet filters would be required in order to make sure that you are that you're killing any sort of microbial life in your in that in the seal support system. You would also have to make sure that your support system is designed appropriately so that it can be cleaned. So maybe instead of using tube fitting connections, maybe you're going to use, quick clamp type, sanitary connections or type connections like that can be disassembled easily, that can be cleaned, that are going to keep your system clean. You make sure that you're avoiding entrapment areas where microbial life could start to collect and flourish. So, the entire system design needs to be evaluated. But in terms of filtration, I would think that some sort of a UV filtration would be appropriate in that in order to help kill any sort of microbial life that might exist in that scenario.
Yeah, great, excellent. Well, unfortunately, we only have time for one last question here, but I will remind everyone that the presenter will get all of the questions and contact info, so he can follow up offline if any of the questions we didn't get to, or if they require a more detailed answer. So I think I'll just end with this question that's probably on everyone's mind. Are these seal pot kits stocked by Swagelok? And maybe you can discuss a little about the services and what's provided there.
Yeah, so the seal pod itself is not stocked. Actually, the seal pod is not something that we generally manufacture ourselves at Swagelok. Instead, we partner with local manufacturers that have an expertise in manufacturing seal pots. So we'll work with them to actually procure the seal pod on your behalf, and then the actual components themselves, for the most part, are to build the system for the most part are standard off-the-shelf components for Swagelok. So when we're putting together a kit for these things, we don't necessarily have the kit on the shelf per se, but we very often will have all of the components separately on the shelf.
Mhm.
So we'll kit those together, put them in a box, and ship them off to you with an appropriate length of tubing, and then also any sort of ancillary third-party products as well. So it could be a strainer, it could be a seal pot, it could be a cyclone separator. It depends on what it is, what it is that we happen to be building. But yes, we definitely can help support you in that. Are they on the shelf? A lot of the components are, but not everything.
Mhm.
But we do what we can to make that be Johnny on the spot, so to speak, with what you need in order to maintain your pumps and your seal support systems.
Yeah, yeah, making it as easy as possible. So great. Well, thank you so much for this great Q&A discussion. We've had so many questions come in. I think this is definitely a conversation that's resonated with the listeners. So I hope that this has just been useful for everyone that listened in today. I want to remind everybody to direct you to the handouts tab for more information there. And then there's also a survey. I think the link is in the chat and it should pop up on the screen here soon. So please do take that survey. Just want to thank everyone for joining us. This program will be archived on Chemical Engineering's website. So if you need to watch it again, it'll be there. Just thank you so much to our speaker, and thank you all for attending. We hope you'll benefit from this presentation. Have a great day.
Thank you, everybody.